Okay, so today I like to talk about basic principle of fluid mechanics. Okay, it's a very fundamental, but not that easy. Uh, uh, Wave mechanics. So I have a reference. It's a book, Water Wave Mechanics for engineers and scientists. Okay, written by R.G. Dean and this is quite famous book. Okay, so can you see the my writing on the board? Yeah. Okay, thanks. Today's topic is about hydrodynamic. Hydrodynamic. Hydro means water, right? And especially I'm focused on the fundamental. Okay. First of all, let me talk about conservation of mass. I like to only consider the 2D case. Okay, 3D case is just the extension of 2D. So I like to drive all the equation for 2D. That's going to be much easier to understand. Okay, what's the conservation of mass? This is really basic principle in physics. And yeah, actually, before the Einstein, make some rule, this conservation of mass was a principle, and this is still principle in fluid dynamics and structural mechanics. Yeah, it means the mass cannot be created or destroyed. Okay, very simple principle. And let me have some volume here. I'm going to consider just x and y, x and g direction here. Okay, this is say the control volume. In fluid mechanics, we always consider the control volume. Inside of this control volume, the fluid will move and get in and get out. So this is a very small volume. It's a differential volume. Size is dx. And dg. Okay. And in this volume, there are going to be some flow u, rho u. Here, rho is density, fluid density, and u is a velocity in x direction. Okay? This is our description. And let's say this is position x0. Then this is position x0 plus dx. I think Dr. Hong lectured about Taylor series expansion, right? So it means if there is a function f, x plus delta x is fx plus partial x partial f delta x, and there is more higher term. This is Taylor series expansion. We know about this, right? And then rho u at tx plus delta t, x plus delta x equal rho u x plus partial x rho u delta x, and we're gonna have a more higher term. Usually higher term is much smaller than these two terms, so we just ignore the higher term because this control volume is very small. Dx and dg mean it's a infinitesimally small length. Okay, this control volume is very, very small. So in this side, we're going to have a fluid rho u plus rho u delta x. Okay, so here rho u is a fluid entering this control volume, and this term is the fluid which get out of this control volume. Okay, and then I'm going to consider the time change. Time change is time change from time equal t to time equal t plus delta t. Okay? And here we can also think the mass inside of control volume. The density can be changed t plus delta t minus rho, okay, delta t equal rho t plus partial t delta t, and higher the term we have. Okay, then let me talk about the mass which flow in the control volume and flow out, and mass increase in the control volume. Okay, so in this 2D problem, first mass flow in and for x direction going to be a rho u, so rho u multiply here x delta y delta g. Yeah, even this is a 2D flow, we can think the depth of that control volume, because it's volume, it's not a surface. And multiply, we need to also multiply delta t. This is going to be a mass. Why this is going to be a mass? Huh? This is density. Rho is a density. It's a m over volume. Okay? And u equal L over t, time, right? And then, okay, this is going to be a L square, this is going to be a t. So, all of this will be a mass, right? So, volume, L, same. Only we have a mass. So, like that. So, this is a mass flow in x direction. And second, mass flow out will be a rho u plus rho u delta x multiply delta y delta g multiply delta t. So this is flow in and flow out. And third mass increase in the control volume. In the control volume. Okay, will be a rho t plus delta t minus rho t multiply volume. So delta x, delta y, delta g, right? Equal rho t delta x delta y delta g delta t, right? So here I only consider the mass flow in x direction and mass flow in y direction, but they're going to be a mass flow in g direction and mass flow in flow out in g direction, right? So we can do the exactly same thing for g direction. Then that equation, so mass flow in g direction will be a rho w. U is a velocity in x direction, w is a velocity in g direction. Multiply. So we have a g velocity in g direction, delta x, delta y, multiply delta t. Okay? That's going to be a mass flow in g direction. And also here, let me see. Okay. Rho w plus g rho w delta g multiply delta x delta y delta t. Okay? So in two-dimensional problem, these are all the mass variation. Okay? Flow in and flow out, and then increase in the mass increase in the control volume. Then to make the mass conserved, how can I do that? Okay, so let me see. Why?
Explain about the right hand side of third equation.
Third one? This one? You hear?
Mass increase in the.
Here.
Is that from difference from equation number 1 and equation number 2? I mean, equation number 2 minus equation number 1 makes the right hand side of equation.
Which one? This one?
Right hand side.
Right hand side, this one. What's wrong? Huh? U is missing? Why?
Is the rho is dependent from spatial?
Yeah, this is about only t, time. Okay? Okay, I'm going to talk about that. So, you know these two, right? This is a mass flow, the mass flow in due to the velocity of the fluid. This is also mass flow out due to the velocity of mass. But this is not a mass change due to the velocity. This is just pure mass change in the control volume. Okay? So, okay. In order to mass is conservative in this system, this is flow in, and this is flow out. And they're inside, they're going to mass increase. Okay, mass change. So this is going to be our equation 1, this is equation 2, this is equation 3. Okay, the mass increase will be a flow in minus flow out, right? Due to the mass conservation. Thinking?
2 minus 1.
Huh? 2 minus 1? Why?
That means
Yeah, this is your volume. So mass is going into this volume. It will increase the mass, right? This flow out will decrease the mass. So this equation means, I think you know about the Reynolds transport theorem. Reynolds transport theorem is 3 plus 2 minus 1, right? Equal 0. Same thing. So okay. So then we're gonna, if you take this, we're gonna have a result T rho equal we're gonna have a plus partial rho u x plus partial rho v, actually w j g. Okay, equal 0. Sorry, this is an equation of mass conservation for fluid. Okay, then let me see here. We can have a different form of this equation. Let me change this equation a little bit. That equation, if you take the derivative for x, this is a function by rho and u. So this equation will become 1 over rho and okay, rho t plus rho partial, yes, if you take rho partial u partial x plus and u, this should be rho plus rho partial g w plus w g rho equal 0, right? Is that right? Okay, then this will become, if we take divide by rho t, okay, t rho plus these two terms. Okay, rho, that term u rho plus w rho plus equal 0, right? Here. Look at here. This is a total derivative of rho dt. Okay? Total derivative. Or material derivative. Okay? Or material. We are saying this is a material derivative. So instead of writing these three terms, we can use only this term. And this term is same to the u. Here is a nabla x g, okay, and u in 2D u w. Okay, then our equation become much simpler. d rho dt plus u 0. This is a equation of mass conservation or continuity equation. Continuity equation. Okay. So now let me talk about material derivative. That's actually quite a little bit the complex concept. I'm going to try to explain as easy as possible. Okay. Yeah, let's assume we have some coordinate system here, and there is some fluid particle here. Okay, this fluid particle will move with some velocity like that. Let's say this position is x. Now this position is x. Okay, this is the initial position. Large x means the initial position of fluid particle. And small x means the current position. This is current position. And density will change as a function of position. Okay? And time. So there is two ways to describe the density function. Two ways. One is like that. One is it can be a function of can be rho is a function of current position and time, right? And the other way is that density can be a function of original position and time, right? So actually, there are some relations between original and current. Current position is a function of original. Okay, we can think this original position is a kind of fixed position. It's a, you can think it's a constant. Okay, then if we take the derivative at the time, in this case, and actually this is not only function of x and it's only also time. So in this case, rho xt and t. Okay, so if we take the, in this case, if we take the derivative, in this case, if we take the derivative over time, the result is just t rho, right? Because here the density is the only function of time. This is a fixed value, right? But in this case, this position is also a function of time, right? It's quite different. So in this case, if you take the differentiation, what happens? Let's take the differentiation. Then it will give us rho multiply x rho. Here the x mean in 2D, x vector mean x and g. So x is also a function of t. We need to use some chain rule. X multiply y rho y t. Okay? This is a total derivative. And t. Okay? Actually, this approach is much simple. Okay? Much simple. The density is only function of time. Very simple. Its reference is fixed. Right? X. Just X. The fixed reference. Here our reference is changing. Because our reference is always current. That's the only difference. So we are saying this is a Lagrangian approach. Lagrangian. This is a Eulerian. Eulerian. Okay. The Lagrangian concept has been used for usually solid mechanics, but Eulerian concept has been used for fluid mechanics because they have a lot of advantage. Okay, for fluid and for solid. Okay, that's a different story. So basically the fluid and solid are both continuum. So they have exactly same governing equation, but the form is different because of this difference in the reference plane. Okay? So I need to talk more about the continuity equation. Continuity equation means just mass increase in the control volume is exactly same to the the mass in minus mass out. Okay? So we have a continuity equation 1 over rho d rho dt plus u equals 0. Here delta u is a volume change. Volume change. This means volume change of that very, very small control volume. Maybe some of you know about that. But we are talking about hydrodynamics, so material is always water. Water is incompressible material. It's incompressible mean. Incompressible mean if you give some pressure on some material, then that material will be the volume of that material will be changed, right? But that change, if that amount of change is very small, then we can say it's incompressible. So for water, we can use this assumption, incompressibility assumption, 0. So, and T low total derivative equals 0. Okay? This is a continuity equation. Continuity equation for incompressible fluid. Stable fluid. Like water. Air is compressible, so when we consider the air, we cannot use that assumption, okay? So that's the really basic and most basic equation for fluid, okay? Then let me talk about hydrostatic pressure. Okay. Hydrostatic pressure. And this is the water level here. And this is G is 0. This is G coordinates. Okay? This is water. So inside of in the water there are some object like that. It's submerged object. Okay? Then in this object there are going to be some pressure applied by water, right? We are saying that's the hydrostatic pressure. And let's say that hydrostatic pressure, the magnitude of the hydrostatic pressure is P. is a function of G, water depth. Okay, this is very well known. Actually, you can prove it's not easy. When we assume the pressure at air is 0. P air is 0. Okay. Actually, pressure is always it relative the value. So, and what this is a P, and important the property of hydrostatic pressure is that it acts in the direction of the normal to the immerged surface. Okay, the hydrostatic pressure always applied normal to the surface. Always normal to the surface. That's the characteristic of the hydrostatic pressure. So, you can define the pressure, magnitude, and the direction at any position in the water, right? This is a direction, and this is a magnitude. Okay? Yeah, let me give you a very simple example. Okay, so G0. Here we have a submerged body here. Okay, its dimension. Let's say this is a 2 meter, 3 meter, and 10 meter. Okay, and the body width is 2 meter. Then we can calculate all the pressure applied all the surface of this body, right? Here at the top surface, the pressure going to be applied normal to the surface like that. The magnitude will be rho g, 3 rho g, right? Because the 3 rho g, and direction going to be a normal to the top surface. So minus g direction here. Okay, how about here? Here we're going to have a much bigger pressure, and 5 rho g. This is going to be pressure upward. And how about at the side? Here 3 rho g, and here 5 rho g. 3 rho g and 5 rho g. Okay, same here also. This is hydrostatic pressure. Let's sum all of these force. You can sum all of these force. Okay, if you let's see the left hand side. The pressure in left side of this body and pressure in right hand side of this body. Same, equal. So, in here in x direction, let's say this is x direction. If you sum the pole, it's 0. But how about the y direction? Sum of the pressure on the top will be 3 rho g multiply the surface of the top surface will be 2 multiply 10. How about here? 5 rho g multiply 2 multiply 10. Okay? The difference is if we sum this, you will have a force in upward direction. G direction will be 5 minus 2 rho g multiply 2 multiply 10. Okay? Then this is the same to the rho g multiply volume of this submerged body, right? What's that? What's that? That's buoyancy, okay? So, okay, so here what I wanted to talk about is that the buoyancy buoyancy force is just a result of the hydrostatic pressure. Acting over the surface of the body, acting over the surface of a body. Okay, and its direction is g. Okay, so some few students think the buoyancy is a kind of a new kind of force, right? But this is just the result of pressure, hydrostatic pressure. Okay, in the hydrostatic pressure, one of our students asked g equals 0. Why the hydrostatic pressure at this point is minus rho gj. Yeah. Okay, so actually I thought most of you know about that. It's very simple to prove. Okay, let's say at this level we have a very small cube like that. Okay, we can calculate the pressure at the top of the cube by the column of the water here, right? the mass of the column of the water will be a, let's say the, will be a, low, and this is a H, and S is here, the area, okay? Then this is a mass of that column, the water column, right? If I multiply the G here, this is going to be a surface force due to the gravity, okay? And if you take the divide by S, this is going to be a pressure. Force divided by the surface going to be a, so this is a low GH, and here the H is a minus Z. So our pressure will be minus rho GZ, right? And then also we can prove the fact the direction of that hydrostatic pressure is always normal to the surface. We can think some triangle like that, this kind, and then we can calculate pressure at these three surfaces, okay? Then using the sum of the force in x direction and g direction is 0, then we can calculate the normal pressure to this surface is exactly same to that P, okay? And okay, so actually this kind of stuff is in our reference. So if you want, then you can just read some part of that reference. Okay, now let me talk about more about hydrodynamics. Here, stress. Now let me talk about stress. Actually, stress is has a quite difficult concept. In my another class, the nonlinear analysis of solid and structure, in that class usually I'm talking about the nature of the stress and then where that kind of stress concept comes from. But this is another that kind of class, so I like to give you just a concept and definition. Now I am only talking about 2D defined by X and G. So we have a rectangle here. This is our some volume of fluid. And here there are going to be some stress. Sigma XX, sigma XY, sigma YY, sigma Y and X. In 2D we have a force stress component. It's a pressure, actually it's a pressure acting on the very small cube. Okay? Usually in this cube there are going to be some pressure with some direction. And this pressure can be divided by two parts, which is the normal component and tangential component. So this is normal component, this is tangential component. If you look at this sigma ij, here the first subscript mean the surface. Surface where the stress act, and this is direction. Surface is can be defined by vector. So this is a surface normal vector. So x direction can define the surface, this surface, okay? And y direction can define this direction. So, okay, surface always can be defined by each normal vector, okay? So, in 2D we have a force stress component like that. So, this stress, actually nature of stress is a tensor. Maybe most of you don't know about tensor. So I like to say it's matrix. We can write down the stress like that. Y, XX. Sorry. Here it should be G. G. Right? XX. Here this should be G. GG. XG. GX. We can write down the stress like that. Okay. So force stress component can be written by a matrix, 2 by 2 matrix like this. One of the very important characteristics of the stress is a stress matrix is a symmetric. Okay. Let's see this component here. If you take the moment at the center of this cube, it should be 0, right? So that gives us the property of stress. The stress should be symmetric matrix. And so, and this is a very important thing. P 1/3 sigma xx plus sigma yy. Here it should be actually 1/2. Okay. Here let's assume the stress in the y direction is 0. Then xgg is something like this. This is the mean stress. We are saying this is mean stress. If you take the mean value of the diagonal component, sum of diagonal component, then we are saying this is mean stress. Mean stress. Okay? This is just average of the stress. And or we are saying this is a hydrostatic pressure. Okay? In 3D, it becomes different. In 3D, so in 3D, stress has a 9 component, xx, xy, xg, and something like that, xyy, gg, or yg. This is symmetric. And mean stress going to be 1/3 xx, yy, gg. Okay? that stress tensor, that stress matrix can be divided by two parts. Okay, like this. Minus pi multiply tau. Okay, so here in this case tau going to be a sigma xx. Then let's see, sigma, tau going to be a tau xx, tau xy, tau, yeah, we are xg plane, xg, gg, and tau sigma xx, sigma xx is minus p plus tau xx, sigma gg is minus p plus tau gg, and sigma xg is equal to tau xg. Okay, so this is a very important equation. Actually, we have exactly the same equation for solid mechanics. So our stress is pressure acting on the surface of the cube. Okay, can be divided by two parts. First one, hydrostatic part. We are saying this is a hydrostatic part. This is hydrostatic pressure. Hydrostatic part. And we are saying this is deviatoric part. Okay. So the relation is like this. You can calculate stress xx by this equation, stress gg by this equation, stress xy by this equation. Okay? Yeah. Yes, right. So now the important process. Let's calculate the equation of motion based on all the information we study to this point. This one, and then the continuity equation. Equation of motion. Okay. Equation of motion is not it's just Newton's second law. Okay. Sum of the force is the same to the mass multiply acceleration. Yeah. Let's say we have some mass here, m. There are going to be a lot of force. Let's say this force 1 and force 2, something like that, and force 3, if I sum of this mass, and due to this force, this will move in some direction with some acceleration a. Okay? In this situation, the Newton laws say the sum of the force will be same to the mass multiply acceleration. This is Newton's law, right? This is just principle. Cannot be proven. Actually, this one equation tells us three equations. Sum of fx equal max. This is Newton's second law in x direction. Sum of fy equal may. Sum of fg equal mag. Right? Because here we are using vector form. This one vector equation gives us three scalar equation, right? Then let me calculate the acceleration in x direction. We are saying u is a velocity in x direction. Okay, to calculate the velocity, acceleration, we need to take the derivative about the time, right? But in fluid dynamics, u is also function of current position and time. Okay? So we are always thinking in the frame of Eulerian. So we need to take the total derivative to calculate the acceleration in x direction u. Okay? This will be a partial t, partial u, plus u plus v plus w. So in 2D, we have only two terms, w partial z partial u in 2D. In 3D, we need to have one more equation, right? Here we are saying this is a local acceleration this is a convective. Okay, but in solid mechanics, u is just a function of initial position, so actually usually u0 t. So we don't have a convective term here in solid mechanics, but in fluid mechanics we have this convective term. And this is acceleration in x direction. So we can also calculate acceleration in g direction, right? Acceleration in g direction, ag will be dt dw, okay, partial t partial u w plus u partial let me see, okay, x, this should be w, so actually something wrong, that's correct, u partial w plus w partial g partial w, right? Actually, in my note, I derived all the equation based on 3D, but for you, I am rewriting 2D equation. Okay? So, this is acceleration. Then let me calculate the equation of motion. It's not that hard to drive. Let's just calculate equation of motion. Equation of motion in x direction. Okay, only x direction. We are in the 2D problem, x and g direction. So here we have a stress here and here. This is a stress component which are acting in x direction only, right? Stress xx. And let's say this is a x0 position. This is a x0 plus delta x. And this is a y0, g0. And this is position g0 plus delta g. So here I'm going to use the lead pen. Here we have a stress xx, and by result of a Taylor series expansion, we will have a stress xx delta x. In this side, here we have a stress gx. Here we stress zgx plus g gx delta g. Okay, and there are going to be also some mass, some force acting on this volume, okay, in x direction. Let's say that is fx. It's a body force. Here the stress xx, gg, and xg is acting on the surface of this cube, right? But there are going to be some force acting on this body. We are saying that's body force. There are a lot of body force, like gravity. Gravity is a body force. It's not acting on the surface. It's acting on the body, inside and outside and surface. For all the position that gravity give us some force. Also, there are magnetic fields. Magnetic fields also give us body force. So this is all the force we have for this small fluid element. If you take the sum of this force in x direction, let's take the sum. Sum will be actually this is a stress. Stress is a pressure. Its unit is pressure. So to calculate the force, we need to multiply the area. So to make a force, we need to multiply area in also y direction. So if we sum all the force, then let's see, we're gonna have these should be deleted. Okay. Then we will have a partial x, delta y, delta g, right? Plus delta x, delta g, delta x, delta y, plus fx, delta x, delta y, delta g. This is sum fx. Okay? Sum fx. The sum of all the fx force in x direction should be same to the m and dt du. This is acceleration, right? Here we know the m is a mass, is a rho multiply the volume, right? Then we can remove all the volume. Then finally we have rho dt du equal xx plus gx, right? X plus fx. This is an equation of motion in x direction in 2D. 2D defined in the x and g plane, right? Similarly, we can calculate equation of motion in g direction dt dw equal partial x xg plus d gg plus fx. Actually, in g direction, we have a known body force. What's that? Huh? Gravity, right? So this Fg. Here Fg is gravity minus g. It's a gravity. Okay. So this is the equation of motion. Okay, so here, this is our final equation going to be minus g. Okay, and usually we don't have this force, body force in x direction. So no, just g. Rho g. Yes, that should be rho g. Yes, that should be rho g, right? Rho g. Let me see. Yeah, rho g. Okay. So this is a equation of motion. Okay. And in hydrodynamic, there are very important assumptions. The viscosity of the fluid is very small. Okay. It means I don't know how to explain that viscosity, right? Actually, here this is a shear stress. I mean the shear stress means here this is shear stress. Shear stress means the stress pressure in tangential direction. Okay? Let's say this shear stress tau. This shear stress is a function of the velocity in that direction. Actually, not a function of velocity, it's a function of strain rate. Let's say this is xg and xg. This is strain rate, and we are saying this is a viscosity of fluid dynamic. Make viscosity of fluid. Okay. Usually in hydrodynamic, we ignore the effect, this effect. So it means we don't consider these two terms here. Okay, we just assume the shear stress is 0. Okay, then our equation become, so we assume tau xg is 0. It means the viscosity is 0. Okay. Then we are going to have a much simplification. Much simplification. Okay. dt du equal 1 over rho partial x partial p and dt dw equal g p minus g. Okay. The equation of this name is Euler equation. Euler equation. And assumption which is made is implicit. Implicit means the viscosity is 0 and incompressible. Actually, this assumption is made here. Okay, so this is Euler equation. Okay.